Hi 242. So we're going to work on an example of Lagrange multipliers, specifically an example working with a Cobb-Douglas production function. So this is going to be matched problem number 2 from your textbook, and that's on page, let me check, 829. It's on page 829, matched problem number 2. So we have a Cobb-Douglas production function, and it's given by capital N here. Okay, and recognize again, Cobb-Douglas functions require that the powers on x and y both add to 1, so we do in fact have a Cobb-Douglas production function. Remember, x represents the number of units of labor, y represents the number of units of capital. We're told that labor costs $40 per unit and that capital costs $120 per unit. So here's the situation. We're given a $300,000 budget. The question is, how do we allocate those funds between capital and labor so that we maximize our production? So remember that production here is the output of this Cobb-Douglas function. So in essence, what we're being asked to do is maximize this Cobb-Douglas production function here. Find the maximum of this function n. But we have to find the maximum subject to the fact that we have a restricted budget. Right? So this is a perfect problem for a Lagrange multiplier technique. We just have to set up what in fact are the parts for the Lagrange technique. So remember that the first step for Lagrange multipliers is always to declare what is the function you want to maximize or minimize, and then also make sure you identify your constraint functions. Okay, so step 1, we can identify the function we want to maximize. Well, that's this function n, because we want to maximize production, right? So we want to maximize n of xy, and we want to do that subject to what? Well, the restriction here is on the budget. Okay, the budget is $300,000. Okay, well we have to then incorporate that budget situation into our costs over here, because we know that each unit of labor costs $40 and each unit of capital costs $120. Well, if we're using x units of labor and y units of capital, then we can figure out just how much we're spending on that many units of labor and capital. Okay, so the total costs that we're going to incur to produce x units of labor and y units of capital will be the following. The cost from labor itself is going to be what? $40 times the number of units of labor, right? Because it's $40 per unit for labor and we use x units of labor. I need to add to that the cost from capital. Well, we use y units of capital, and capital is $120 per unit. So the cost there is 120 times y. Again, 120 per unit for labor, or for capital, times the number of units of capital. Remember, our budget says we have a $300,000 budget. Well, we're going to use all of that budget here. So again, that's our constraint function. And we need to make sure that we have all of our units in the proper way here. It says in the problem that we're not considering anything in terms of thousands or anything like that, so it's okay for our constraint here to be equal to 300,000. Okay, so what that means here is that our g of xy, our constraint, is 40x plus 120y minus 300,000 equals 0, because remember, we want our constraint function set equal to 0. All right? So we've identified the function we want to maximize, that n of xy, which is written up there, subject to this constraint. Now we can proceed with the Lagrange multiplier technique. And remember, the next part is to find some partial derivatives and set up the system. We'll leave this here for just a second. Okay, so step 2 is to find the partial derivatives. So I'm going to need to find nx, ny, gx, or wait, yes, nx and ny, yes, and then what? Gx and gy, and then we'll have to construct the system. So what is nx? Nx is the derivative of this expression up here, where we think of x as being a variable and y as being a constant. Okay, so that means we have 20 times the derivative of the x is what? 0.5, x to the negative 0.5. Bring the power down and subtract 1, and the y acts just as a constant. Okay, it's stuck around for the same reason the 20 did. Simplifying a bit, this is what? 10x negative 0.5, y 0.5. And similarly, the partial derivative with respect to y of the Cobb-Douglas will be 20 x to the 0.5 is a constant, and now the derivative of y to the 0.5 is 0.5 y to the negative 0.5. And again, simplifying, the 20 and the 0.5 can interact because this is all multiplication here. So this is 10x to the 0.5, y to the negative 0.5. Okay. So now let's find our partial derivatives of g. So we have g sub x is 40, and g sub y is 120. Our Lagrange technique will tell us that I take these partials and I set up a system, right? I have to include that lambda character here. So the system that we're going to construct is don't worry, I'm not writing something that you need to see. I'm rewriting. I was writing down our constraint over here so that I can erase it and then use it again in a second without having to use up board space for it. Okay, so let's construct our system. So remember, this was n sub x, and this is n sub y. Okay, so let's construct our system. Okay. Our system will say I do n sub x plus lambda g sub x equals 0. So I have 10x to the minus 0.5, y 0.5 plus lambda times g sub x, which is 40, equals 0. And I'm going to erase these as I move a little at a time here. Again, remember, you can pause the video. There's our first equation. Ny is 10x 0.5, y negative 0.5 plus lambda times 120 equals 0. And now we have to add as our third equation the constraint, which is 40x plus 120y minus 300,000 equals 0. And this specifically is our system that we're going to solve in order to find our candidate points. So remember, the thing I taught you to look for, first of all, is a good first step is to try to eliminate the lambda. So notice that in these first two equations, you could actually solve each of them for lambda, and then we could set them equal to each other. Okay? So let's do that with the first one, and we'll see what we get. If we solve for lambda in this case, that would be the same as doing what? Subtracting this expression over to the other side and dividing by 40. So I would get lambda equals negative 10 x to the negative 0.5 y 0.5 over 40. And in the second one, I would get lambda equals negative 10x 0.5 y negative 0.5 over 120. Since these are both equal to lambda, I can set them equal to each other. And here's where the trick will come in. I'm going to erase this part over here so that I have some space to work with. That's the problem of having a small board. Okay, so I now set these two things equal to each other. So I have, you could of course simplify, I'll do that in a second, but I want to just see how the equations look when they're set equal to each other. That's the two equations set equal to each other. Now, if we do a little bit of simplification here and interpreting what these negative exponents here mean on the x on the left side and on the y on the right side, I could write this as follows. The 10 and the 40 could cancel to leave just a 4 in the bottom. And the x here with the minus 0.5 wants to be in the denominator. So when I do that, I'm left with minus y to the 0.5 over 4x to the 0.5. Okay, again, the 10 and the 40 cancel to leave the 4. Negative sign. Y wants to stay up top, and the x here wants to be in the denominator. And on the right side, I have, again, a negative sign. 10 and 120 cancel to leave a 12 in the bottom. X wants to stay up top, and y wants to be in the bottom. Well, the negatives, notice there's a negative on each side of this equation, so we could actually just get rid of that negative sign as well. and make our lives a little bit easier. And now we have a proportion, and how we can actually solve a proportion is by cross-multiplying here. All right, so let's do cross-multiplication, and when I do that, I will have 12 y to the 0.5 times y to the 0.5 equals 4 x to the 0.5 x to the 0.5. And what happens when we have these two bases multiplying? We add the exponents. So this is 12y equals 4x. And we could even make that look nicer by writing 3y equals x when I divide both sides by 4. Good. All right, so what do we do with that? Well, don't forget, I erased it already, but there's another equation in this system of equations. We have the equation coming from the constraint that we still have to use. And remember, that's the whole point of this technique, is that we take this system and simplify it down to fewer and fewer equations until we can finally get a result for x and y. So now what we do is we use the following two equations together, 3y equals x, and the constraint, 40x plus 120y minus 300,000 equals 0. So notice I can take this first equation, and by substitution I can put it into the second equation. So we can write substituting, we get the following. Replace any x you see with 3y. So we get 40 times 3y, because that's an x, plus 120y minus 300,000 equals 0. And of course the only unknown in this equation is now y, which we can solve for. This is 120y here, and this is 120y here. So when we add those together, we get 240y equals 300,000. Okay. When we solve for y here, we get 300,000 divided by 240. Which is 1250. So what we have now is a value for y, and now what we need to do is get a corresponding value for x, right? We need to figure out what would be the corresponding value for x. And notice that we can use any of the equations we like that are a relationship between x and y. But I think this one right here is going to be the simplest one. Remember, that's the one that came from using those first two lambda equations together, right? So this will help us here. If we know y is 1250, well, then 3 times y has to be x, right? That's what this equation says here. And what is 1250 times 3? Well, that would be what? 3 in the front, and then this would be 3750. 250 plus 250 is 500, and 250 more would be 750 with a 3 out front. So we have our candidate point. It's the ordered pair 3750, 1250. And since we only arrived at one candidate point, we can assume that's the one that is going to maximize the production of whatever it is we're making, right? It's going to maximize the production function. And so if they ask you, what is this maximum production? Well, that means we just need to evaluate the production function at this given critical point. That'll be n of 3750, 1250. And I'll allow you, you can just plug that in and evaluate it yourself. Okay, good. So there is one piece of information here that is relevant. Usually the lambda doesn't have meaning for us in these problems unless you're doing a Cobb-Douglas production function problem. In a Cobb Cobb-Douglas production function problem, when you do maximize it using the technique of Lagrange multipliers, the lambda actually has a specific meaning. So in these problems, it turns out that lambda is actually what's called the marginal productivity of money. So, and we need to be specific, it's actually the negative of the value of lambda. So we'll say the negative of the value of lambda is the marginal productivity of money. And what does it do? It gives the increase in production for each additional dollar spent on production. And similarly, we have ways to interpret the partial derivatives of the Cobb-Douglas production function. Remember, they were the marginal productivity of labor and the marginal productivity of capital, right? The effect of those, the number of units of labor and the number of units of capital changing have on production itself. Okay? So whatever, you can get a value for lambda by evaluating the lambda equals equations when you solve them in the first part of trying to eliminate a variable in the system. You get a lambda equals equation. You can figure out the value of lambda by replacing x and y that we got, 3750 and 1250, into that lambda equals equation. It'll give you a value for lambda. And that'll be the marginal productivity of money. We'll talk more about this tomorrow during class.